All right, guys, I'll put the stuff down here for the first one, whatever the hell that comes out to be. Right, and this is definitely pi over 4. I'm in the xy plane in the first quadrant, so pi over 4 is all I need there. Here, what do you guys get? You get rho equals 9 plus 3 plus 8. Square root of 20, which is 5. And then I guess for theta, it's going to be the inverse tangent of y over x, so negative rad 3 over negative 3. That's an angle you should know. The negatives cancel out, but you've got to pay attention to it because it tells you you're going to be in what quadrant? Third quadrant, right? Negative, negative, third quadrant. So when you do the inverse tangent of that, you get the reference angle comes out to be pi over 6, and then you just got to throw it to the third quadrant. So it'll be 7 pi over 6. Pi over 6 more than pi. So if you threw it in your calculator, you got a decimal answer. Bleh. Let's see that shit. And then phi or phi, whatever way you feel like. Phi or phi. The inverse cosine of z, 2 rad 2, over rho, 2 rad 5. So the inverse cosine of rad 2 over rad 5, whatever the hell that is. If you just leave it like that, I'm happy with that. So that's the exact answer. And then whatever engineer needs it to whatever tolerance, you can take it to whatever tolerance you want to. I'm not going to decide for you. That's why we like to end up in the exact answer, so somebody else can round it to whatever they need to. Is that cool? You guys is cool with that? Please let that be good. All right. Now this is just going the other way around. I just gave one of them because it's pretty simple. X, what do you guys get for that? It'll be rho. Rho is 9. Sine of pi. I like it. And then cosine of pi over 4. That's of course 0. In fact, we already know going in, since phi is pi, I'm going to be on the, like we said earlier, since phi is pi, I'm going to be on the z-axis, right? I'm going to come all the way back to the z-axis just down here. So it makes sense. X is 0, y is going to be 0. Gives you 9. Again, sine pi, blah, 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 equals 0. Z is going to have to be, so, yeah, now it's 9 cosine pi of negative 9. There you go. So it's just a point, 0, 0, negative 9. This one, we saw one like this on that polar coordinate handout I gave a while back, where secant is just 1 over cosine, so you throw that up there, and that's exactly one of the translations. So if you multiply by cosine, you get rho cosine phi equals 2. Rho cosine phi is z. And that's not a point, so a few of you guys were worried about the other ones. That's the equation of that surface. Right? There's an equation, it comes out in the equation, it's not a point, it's just a plane. That's that surface. What about number 4? True. So if I take the what of both sides, that's a good first start. Yeah, take the cosine of both sides. So I get, and cosine phi is going to be what? Z over rho. And cosine of pi over 3? 1/2. I like it. So z equals 1/2 rho, and of course rho is well, that's as far as I'm going to ask you to do it for right now, but you can imagine you could square both sides, get your z stuff together, get some kind of a slightly better function for that, a better equation for that. That's plenty. You guys see that? Is that cool? Okay. Because to be honest, we could write this as z over the square root of x squared plus y squared plus z squared, right? Yep. That's actually a little more accurate because this is kind of like putting a spherical in where there should be rectangular, but it's just a much nicer, compact way to write it. And then finally, this guy, it's a cylindrical. What would that be?
R squared.
Yeah, z equals r squared. I mean, come on, that's awesome. Well, what about spherical coordinates?
R cosine phi equals R squared sine squared.
All right, so z is r rho cosine phi, right? Equals.
X squared is rho sine phi.
Yeah, but watch this. I want you guys to notice something. Isn't this going to be, well, I mean, it'll come out the same way either way. But isn't this x squared plus y squared plus z squared minus z squared? And what's x squared plus y squared plus z squared? Rho squared. And what's z squared? Rho squared cosine squared phi. Natural. And then, of course,
No, that's rho.
what's rho squared minus rho squared cosine squared? It's rho squared
One sine.
sine squared.
Oh, dude. What?
And then you get rho. You can cancel a rho out. You can divide by sine squared. Cosine over sine is cotangent. And 1 over sine is cosecant. So, I mean, that's one way to write it. Now, if you plug in directly for x and y, you eventually should get to the same place because x squared plus y squared, won't you be able to take that out? And then don't you get a cosine squared plus sine squared?
You're too high.
Oh, sorry. Whee! If you put x squared plus y squared, you can take a rho squared sine squared phi out. Cosine squared plus sine squared is 1, so you end up with rho squared sine squared phi, just like I did. Same thing. Maybe. Anyway, so, I mean, this shouldn't be that horribly evil. Spherical is certainly brand new, a few parts of it, so you should play around with it to get used to it. Next thing. Any questions on that, by the way, before I leave this alone? Any questions on freakiness here? No. All right, so obviously, this is not Math 281. This is not, because somehow I got to bring in integration, right? Triple integrals for cylindrical is going to be nice. We already did cylindrical, triple integral. This guy, oh shit. And you need a visual aid here because there's no way in hell I'm going to subject you to me trying to draw this. So the idea, remember when we did polar and we had a polar rectangle? Right? Sounds like some really poor analog to the Polar Express or some horrible movie. We did the polar rectangle. And remember, where'd that extra R come from? Where'd that little hanging R come from? Why did we need that? R, dr, d theta. What is that actually? That R is actually with what officially? D theta, because it actually gives it length. Right? So arc length is R theta. I like it. So a similar thing's going to happen here in a few different directions. How many angles do we have in spherical? 2. So there's actually, the integral, it should make sense, it's going to end up with a rho squared in it. Because there's 2 angles that have to be multiplied by rho to give them actual length. The same way we had to multiply d theta by r to give it length, so it ends up with an area. Right? Here I'm going to have to multiply it by 2 rhos to give it a volume. Oh shit. So here's what it looks like. Here's what it is. So the polar rectangle now becomes, in spherical, a spherical wedge. There you go. Okay. So, I mean, this is in your book. I always see this as kind of like a hammer. You guys see that hammer?
Oh, yeah.
And you're like standing here. Calculus. So just to cut to the chase, I was thinking about printing out a blank one of these and forcing us through all the machinations of all this shit. But I want you to notice how it's really the same argument we used with polar, just in 2 places now. Here is just delta rho. There's just no question about that being delta rho. That's the direction I'm going. That's the axis I'm following there. Is that cool? That side is delta rho. Okay, we got to start there. This is phi. That's delta phi, but to make it an actual length, I have to multiply it by rho. All right, I like it. I like it. So this is rho delta phi, the same way that in polar it was r d theta. I like it. I like it. And these are all going to become d's when we do the limit and all that kind of stuff. Same stuff that you've done before. Look at it. And then finally, this side here. So I need height, width, and length to get the volume of this box. So we got this, we've got this. Now I just need this piece, and I really have to transfer it down here. I can see that's delta theta. And of course I got that rho sine. That's really what it is here, rho sine. That's the length times delta theta. So that's going to be here. So what you end up with, after all that, and your pictures in the book, you really should be able to kind of piece that together for yourself. It's not that far a step from what we did with polar. What do you end up with in the end when you put all that stuff together? What's dV going to be? I don't know. Let's find it. So we got, let me try to draw this. It's going to be exciting. Sure, man. That's better. For me, that's really, really good. So there's delta rho. This little piece here is what we just did, the last one, rho sine phi. Let me go ahead and make it d's. D rho, d theta. And this one is going to be rho d phi. So when you put it all together.
Is that partial D? Theta?
Oh, I don't know why I got stuff on it. Oop, let's not make it too crazy.
That's partial rho up top, right?
No, that's definitely just d rho.
Or zero, that's right.
Yeah, so we get rho squared sine phi. That's related to, that piece there is related to the r that you put in for cylindrical. Are you guys with me? So officially there would be like an f here, right? An f of rho theta phi. Right? But if I do this, it would actually end up with a volume. There is a 1 here if I don't put something else besides this. So this is just like that extra r. It's a part of dv. So we start with integral, dv. And dv, this is a part of it. Oh shit. So I got this, and then I need d rho, d theta, d phi, or d phi, d theta. This book, I think, does. Let's keep it the same. Books are always different. It does d theta, d phi. Yeah, good. That's what it did. See, you have an example of that here. Bless you. Let me give you the real official deal here. Well, this is, we don't have, if we have it, let's do the more general one. There's a more general one. But here you can at least see the end of it being what we said it would be. This little piece here. Did they give me the more general one?
Also known as a big ass snowflake.
What's that? Now these, for some reason they have here that these are, they look like constants, but they don't have to be constants, guys. They could be, functions themselves. I don't know why they give it. Yeah, so here's a good example. Be a function there. And I want you to notice something. Some of you guys, there's a really, really basic idea that I tried to capture quickly, but hopefully it came out in the conceptual discussion. But normally that outer integral almost always will have what type of limits? Constant, right? Numeric, some kind of scalar level, not a function. The most inner integral here, what could it be a function of? Rho, phi, all three of them, right? Now the first thing I do is d rho. So what could not be here? What could this not be a function of? Rho. Because rho should be completely determined when you get that inner integral done. You guys see how this kind of stacks so that you can take a step back from the integral you set up and just see, does it make actual mathematical sense? I'm trying to tell you, some of yours didn't make any sense because you have the outer one had functions on it. No. It's got to come out to be a numerical answer to the problems that I gave you. Anyway. All right. Maybe. This is a good example of how to do one of them. Look at let's do, just going to keep hyping on Jim Carrey's sphere here. Number 23. Well, like you. Let's just do this. We don't have the most time left, but let's try to set up what the integral is going to look like for this problem. Number 23. This is still 15.8. Spherical, yeah. Spherical, yeah. I think you have the case as a multivariable calculus. It's not.
Sorry to tell you, test came back.
Calculus is a condition of the teeth. You got multivariable calculus. What happened? Oh, what other one? Yeah, there's only, this is a nice one to start with because let's see what we can figure out. Since they don't specify an octant or something, both angles are going to go through their whole range, right? So phi is going to go from 0 to pi. And some people get hung up on, well, that's half. Well, I get the whole thing when I spin that because of theta. This just goes this way, theta spins it. So you get a complete sphere then. So phi is going to go from 0 to pi. Theta is going to go from 0 to 2 pi to get the complete turn. So those together, they work together. That's why this one only has to go from 0 to pi, because the theta gets whatever rotation it needs. Where am I at? So rho is the only thing you really have to worry about, but rho goes from what to what? 2 to 3. Yeah. You guys with me? Number 23. So when you set this up, it would be... Now the inner one, what happens to the inner one? We just did that one. This is dV. So rho goes from 2 to 3. Theta goes from 0 to 2 pi. Phi goes from 0 to pi. What's going to happen to x squared plus y squared? Oh, R. I don't want to hear R. Sure. Rho squared minus rho squared cosine squared, which is rho squared sine squared. We just did this one, right? X squared, so it's rho squared sine squared phi. Now notice you'll get a sine cubed phi. Oh, some 280 shit coming at you. So don't forget about that. Anyway, so that's just setting that up. Integrating that should be relatively straightforward. Last thing for today, and then I'll let you out of here. We're about to get into this kind of stuff here. So hopefully you guys have seen stuff like this before, maybe? This is just a wind map. Oh, there you go. It's a little bit better. So we can zoom in. Ooh, look at that. Ooh. Now notice how this wind here, see this let me see, this little guy here. Oh, what I'm doing. And of course, what does that denote then? It's not very strong, you know. So that these now they do curve, which is sort of well, we'll see. These are almost equivalent to an idea of what's called a vector field. So whenever you hear in a science fiction movie force field, they exist. Force fields exist. Not exactly quite like they have, right? I can't say that. But you know, sort of like when they blow the wind in the doorway so that no hot air comes in. You've gone into some place like that. They've set up kind of like a force field, you know, so bugs and stuff get turned away, and the heat gets turned away. So these are actual little vectors. So what vector fields do is every point in the xy plane, to start with, has a vector associated with it. So there is a function that defines what x and y do to make the x coordinate and the y coordinate. So, for example, in the sheet I just passed out, oh, geez, multimedia and multi-calculus. There's too many multis.
Let's go back to size.
There you go. So there's a function. This is a vector function. It's a vector function because the output's going to be a vector. So every point in 2 space is going to have a vector associated with it. So, for example, at 0, 0, it's 0. At 2, 2, what would the vector be? So at 2, 2, that's the tail, I would draw 1, 1. I would draw like this, there. Right? So, of course, as I get further and further away from the origin, the vectors are going to get... As x and y get bigger, they're going to get bigger. I like it, right? Does that make sense? So now our inputs are going to be points like we had before, but instead of going to a surface, they actually they're part of a vector. So the outputs are going to be vectors. And you draw them from the point you plugged in the direction with the length that you got out, right?
How do you know which way it is?
Well, because what vector do we get when we put 2, 2 in? We got 1, 1. There's no question. 1, 1. There. There's no question about what direction, because it is a direction. If I went the other way, it'd have to be -1, -1. So vectors have that information in them. Don't forget that. It's completely defined. So that's where we're headed to next, into chapter 16. Oh, shit. Yes.